I'm Professor Angela Rasmussen, and I'm from the Department of Electrical and Computer Engineering at the University of Utah. I'm going to go over a BJT doing some AC analysis examples. So this is going to be the circuit that we're going to look at. So it already has the hybrid pi drawn for it, and we're given information about our pi 1 and the DC current IC2. So from this, we're going to need to get the other AC parameters, such as our pi 2 and GM1 and GM2. So the relationship for GM1 for our pi 1 is a beta over our pi 1. And so we have, in this case, beta is given as 100, so we have 100 over 4,000, or 4K. And so we get that this value is 25 milliamp per volts. So this is going to be our GM1 value. For GM2 and our pi 2, we know the relationship between GM and IC is going to be IC, the DC value of that, over VT, which is your thermal voltage. And again, at room temperature, about 26 millivolts or 25 millivolts. I used 25 millivolts. So I had 5 milli over 25 milli, which is 0.2 amp per volts. So 0.2 amp per volts for GM2, and then we can either convert IC2, which is a DC value, assuming again this is active mode, so only can use the hybrid pi in active mode. So we can either relate that to IB, and then our pi is VT over IB, or we can use GM is beta over our pi. And so solving that for our pi 2, we would have 100 over 0.2. And so this gives us 500 ohms. So these will be the values for the AC parameters that are in this circuit. So we want to now solve for Rn, Rout, and the midband gain, which is the output over the input Vsig. So let's start with Rn as our first one. So with Rn, we want to identify where we are located, which is going to be here at this node. We want to try to remove this, and so we're going to use the resistance reflection rule. Our location is in the emitter, so this is the emitter side, which means we're going to reflect into the base. So these would be divided by beta plus 1 for each of these. And then our pathway goes from Rn is going to go just through here to get to ground. So that would be, and then we're ignoring the source input, which will be this when we're looking at the equivalent resistance. So just ignore that for the equivalent resistance. So Rn here is going to be 100 plus 100 plus R pi 1 over beta plus 1 plus 100 over beta plus 1. And then we can plug in the value for our pi 1, which was, go back up here, 4,000. And our value for Rn is 241 ohms, which is a great low value, which is not ideal. Typically, we want a high Rn, and so this would be considered very, very low. So Rout, we see that it is located on the collector side of this. And so we have, at this node, we have two different pathways to ground. There's going to be one here and one here. And so we're going to have those two paths in parallel. So Rout will be 2K in parallel with this other branch on the 4K side. As we go through this, we see another split. The 2K here goes directly to ground, but the 2K here goes to the top of the transistor, and remember that that looks like an open. So if that's open, that's ignored because it's just a floating 2K resistor now. And our pathway will just be a 4K plus 2K is 6K in parallel with that 2K. And that will be 1.5K ohms. So the other information we want is to get V out over V sig, which is located over here. I'm just going to erase these for a minute while I am, oops. All right, so now I'm going to write an equation for this V out node. So if I know the current in this branch, I can take current times that resistor of 2K. And so that current is going to be a current divider between this branch and this branch. And so in the bottom branch will be 2K and the other branch will be 6K. So writing that out, it's small enough to see, let's see. V out is going to be a minus GM2 V pi 2 times 2K all over 2K plus the other branch, which is 4K plus 2K. Remember that other 2K that is above this 2K here, you ignore because it's got the same current going through this branch from the dependent current source, so that will be ignored. So plugging in the values for GM, GM2 was 0.2. And then multiplying that out, we end up with V out here is about a minus 100. Oh, and I did forget. This is only the current, and then I need to multiply it by 2K. And so this is minus 100 V pi 2. And now I need an equation for V pi 2. V pi 2 is located here. And so we want to try to ignore the dependent source of the same transistor. So we're going to try to remove that one, which means that our location is going to be in the base side of this. And so we're going to reflect the emitter transistor by multiplying by beta plus 1 on that transistor. So from there, again, we can use the current in this branch now times R pi 2. And so that equation will be V pi 2 minus GM1 V pi 1 times 200K all over 200K, which is one branch, plus the other branch, which is 200K plus R pi 2 plus 200K times beta plus 1. So that is my current, and then I multiply it by R pi 2. So now plug in the values for R pi 2, which is 500. This is 500 then. And GM1, which was 25 milli. So plugging in those values, multiplying that all out, gives a value of minus 0.121 V pi 1. So now we need an equation, oops, sorry, this is V pi 2, is equal to that. And so now we need V pi 1. And V pi 1 is located in this transistor. We want to ignore this one. And we locate our source, which is in the emitter side, which then we would divide the base resistors by beta plus 1. And now this is a voltage divider. This is plus to minus and plus to minus, so they're going to be in opposite. So I'm going to get a minus in this voltage source. And so V pi 1 is going to be a minus V sig times r pi 2 over beta plus 1 all over, I'm going to combine the bottom, which would be 200 plus r pi 2 plus 100. Both of those are over beta plus 1. And I can multiply that out to get a minus 0.164 VSig. And now I can go back and plug these all in. So this one is going to be a minus 100 times V pi 2, which is a minus 0.121, V pi 1, which is a minus 0.164 VSig. So finding a spot to write on, go down here. So V out is equal to the minus, it ends up being 1.98 VSig, and then I can just divide the VSig to get VO over VSig. So that ends up being minus 1.98 volts per volt will be my answer for this one. And that concludes my solution. Thank you for watching.